Hello everyone, welcome to another class of fundamentals of particle and fluid solid processing. In the last class we have seen the motion of a single particle in an infinite pool of liquid. We will be continuing on that concept, and as I told in the last class that we will be having some worked out problems here. But before that, few necessary concept again has to be cleared. So in the last class that I mentioned that when a particle is falling under gravity in a infinite extent of a pool of liquid, or let's say the fluid, we have seen there are 4 regions that we are able to identify, or the researchers had identified. One, for the low Reynolds number, there was a Stokes law region, then there was an intermediate region, after that we had Newton's law region, and then we had, for the higher Reynolds number, we had boundary layer separations region. So in this Stokes region and the Newton's law region, CD calculations, or the drag force coefficient calculation, coefficient of drag calculations, was pretty easy, okay, or there were established correlations, or there are established correlations that helps us to estimate what could be the drag coefficient in Stokes law region as well as in the Newton's law region. But in this intermediate region, we mentioned that it is fairly complex, and after several experiments, researchers have come up with a several various correlations that broadly can be categorized in this manner, that this terminal velocity in the intermediate region is proportional to the particle diameter to the power 1.1, the relative density to the power 0.7. So basically these are the parameters that influences and to this magnitude to the terminal velocity when it is settling, or it is falling under gravity in a pool of fluid without any boundary influence. So now the problem I posed, that there can be 2 scenarios. In one hand, you have to calculate the terminal velocity of a known size particle without knowing its settling region, or the scenario can be that you have to find out that what is the particle diameter for a given terminal velocity, but again in this case you do not know in which region that terminal velocity is mentioned. So to estimate such problem, or to calculate such problem, what we have proposed, or the solution was proposed, that if we find out such parameters, okay, and CD REP square and CD by REP, that actually results into some non-dimensional number and a constant parameter on the right hand side, that is, in this case, this is independent of terminal velocity, this expression. So which means this parameter in a log scale, CD log CD versus log REP scale, will produce a straight line of slope -2 that will intersect the standard drag curve, and from that we can calculate, or we can estimate the particle Reynolds number. Once the particle Reynolds number is known, all other parameters or the physical properties are known, and we can find out from the particle Reynolds number expressions what is the terminal velocity for that given size particle. Okay, so we have seen this logic in the last class. Similarly, when we have to calculate the particle size without knowing its settling region for a given terminal velocity, this expression, calculation of CD by REP, actually results into an expression where it is independent of the particle size. There is no mention of x. So now this plot, log CD versus log REP on the standard drag curve, will result in a straight line with a slope of +1. Okay, and from that intersection we can find out what is REP. From the expression of REP we can find out what is the value of x. In this case, this is the positive 1 slope and this is the x, this is the negative 2 slope. There we can find what is the ut. So, using this combination, we can find out. And another thing that is that these are the constant values for a given particle and the fluid system. This parameter particularly, this is dimensionless quantity, is sometimes called, in fact called, the Archimedes number. Okay, so we have introduced another non-dimensional number like the Reynolds number, which is the Archimedes number in this case. Okay, so in this case, this is another constant number, although it doesn't have any name, but the scenario is that this yields into a constant value for a given particle and a given terminal velocity. Since this property is independent of particle size, for any given system we can find out this constant value and can have such plot, which will give us the required value, or we can detect the Reynolds number, particle Reynolds number. From that we can find out either its diameter or its terminal velocity, whichever will be unknown. Now, the things that we have talked about was the spherical shaped particles, okay, but in reality there are non-spherical particles. So, what will happen in case of non-spherical particles? Now, how do we characterize non-spherical particles? Although we mentioned this extensively in the first section of this course, let me again tell you that typically any irregular shaped body, okay, we find out its equivalent diameter. Now, the equivalent means, how do we find an equivalence? It is typically quantified by a number called sphericity, which quantifies the shape of a particle. Okay, we can have a sphericity by such definition, which is defined as the surface area of a sphere of a equal volume to that of the irregular shaped object, okay, divided by the surface area of that non-spherical object. Okay, so which means, let us say we have a cube. It is a regular shaped body, but still it is not a sphere. But sphericity is a measure that how a shape of object is deviating from the shape of a sphere, how much it is different. That is quantified by this parameter called sphericity. Okay, so for a cube of, let us say, side length 1 unit, okay, the volume is 1 cubic unit and the surface area is 6 square unit, okay, or unit square, whatever the unit you can choose. Now, by definition, the sphericity says the surface area of a sphere having the equal volume of that irregular shaped particle or the object. So, which means a sphere having 1 cubic unit in this particular example will have a certain diameter, and that diameter we can calculate as 1.24 unit. Now, this sphere of diameter 1.24 unit, although it has a volume of 1 cubic unit, but it has a different surface area than the square unit. Okay, so that surface area is basically 4.836 units of the square unit. Okay, then the sphericity of cube is defined by definition is that this value, okay, which is the surface area of a equal volume sphere divided by the actual surface area of that object, which is here 6. So, sphericity of a cube is 0.806. Similarly, for any such irregular or a regular shaped particle other than sphere, we can find a sphericity value. Okay. Now, this sphericity is a measure of how non-spherical object that is. Okay. So, it is a determining factor, or it is a determining characteristics of the particle shape. Okay, and then comes the equivalent diameter. So once you have that, okay, so basically equivalent diameter, sometimes we have seen several cases in the previous section that it can be the surface mean diameter, volume mean diameter, mean volume diameter, mean surface diameter, and several such parameters. Okay, so again problem specific, in a problem specific manner we take whichever is more appropriate such equivalent diameter. Okay, and now here we have seen how irregular shape can be quantified. Okay, now this shape basically influences this drag coefficient more in the intermediate region than this Stokes region. Okay, so the shape basically influences more in the intermediate and Newton's law region. In the Stokes law region, what happens or what has been typically observed, that this particle falls with its longest surface nearly parallel to the direction of the motion. Okay, and but in Newton's law region it has been seen the other way around, that the particle falls exposing the maximum surface area to the fluid. Okay, for sphere this is irrelevant, but for the non-spherical object you can understand that there will be certain surfaces which has the maximum surface area than the other side, or let us say the frontal area is higher than the rear side, or the rear side. Then what happens, let us say the side 1 has larger surface area than the side 2. Okay, and side 3, let us say it's possibly the lowest surface area that is available for that particular object. So in case of Stokes law region, that particle will fall with its longest surface, okay, that is the side 1, in parallel to the direction of the flow. Okay, but in Newton's law region, the surface 1 will possibly be exposed to the motion of the flow. Okay, so you can now understand in which cases the drag will be higher. So with this influence on the non-spherical particles, because now if it's not spherical, its orientation matters during the settling or rising through a pool of liquid. Okay, so and how it settles or rises, that we have seen here. This is the common observations that has been done in the Stokes law region and the Newton's law region. So typically, again, like the other cases, this is typically quantified by such plots or the tables that are given, where the particle Reynolds number in this non-spherical object are based on the equal volume sphere diameter. Okay, because here you can understand when it is settling or rising, it is the displacement volume or the buoyancy force that becomes one of the determining force. Okay, so it is the volume, the equivalent volume of the sphere is that what matters. Okay, so REP is typically based on the equal volume sphere in this case, and the diameter of the sphere having the same volume as that of the particle. So, and in some cases we have seen the sphericity may not be a sufficient condition to demonstrate or to identify the shape of a non-spherical particle. Why? Because you can understand that the sphericity value, let us say the 0.8 that we have seen for a cube, it can be of a irregular shaped particle. Okay, somehow let us say the numerator and the denominator matches in that case, or let us say the overall value matches of 0.8. Okay, and then in that case what happens, it is not a cube, but by that value if you determine that as a cube and then calculate the drag force or the surface area exposed to that, your calculation of the design may be wrong. Okay, so the point is that the shape of the object identification is important, but in absence of that, in case of bulk amount, we typically consider the sphericity, okay, by a factor which is deviating from the spherical shape. Okay. Now the drag coefficient versus the CD versus RE curve in this non-spherical particles also, depending on the sphericity, there are several curves available or several lines are available. Okay. So here also it can broadly be categorized in 4 regions: the constant region, intermediate region, as the 24 by REP, that kind of a region, intermediate region, a straight portion of that, the Newton's law region, and then there is a boundary layer separation region. Okay. So sphericity 1 means this is for a perfect sphere, and as it deviates, the CD versus RE goes like this. So again, x axis is the single particle Reynolds number, and this is the CD. So this is the schematic of this. The detailed value based on the different shapes can be found in the textbook that has been referred or mentioned in this course brochure. Now, to give you a number that how it happens, or how the non-spherical particle or let's say the spherical particle settles. Okay. So the point is that to give you a number of how this size and the terminal velocity is dependent. Okay. So here this is to give you a feel based on the numbers. So this is the sand particles of density 26 kg per meter cube is falling from rest in air. Okay. If the sand particle is of 30 micron diameter, it reaches its 99% of the terminal velocity, or which means it attains a kind of equilibrium. We can consider its terminal velocity at that point is 0.07, and the it traveled a distance in this time is of 0.00185 meter, which is 1.85 millimeter. Okay. So it takes 0.033 second to reach its terminal velocity when falling in air in ambient condition. At that time, it attains a value of 0.07, which is its terminal velocity, and by then it travel a distance of this much, 1.85 millimeter. So this is a 30 micron sand particle. Okay. Now if this becomes 3 millimeter size particle, okay, the time it takes to reach the terminal velocity is 3.5 second. The terminal velocity attained is 14 meter per second, and by that time we reach that particle travels a distance of 35 meter. Okay. 3 centimeter sand particle time takes to attain its terminal velocity of 44 meter per second is 11.9 second. Okay, and by that time it would travel 453 meter. So you can understand, as the particle size goes bigger and bigger, what happens is that Stokes law region ceases to exist. I mean, in particular, let's say a lab scale experiment, because this is going to be a very high Reynolds number. Okay, and the time it takes becomes considerably high, and by that time it travels a lot of distance. Okay. So the point is that if you are doing some experiment at the lab scale, that the settling or some kind of an experiment with the smaller particle, it quickly falls or quickly attains its terminal velocity. So you can consider that now it is falling at a steady state or a steady rate, okay, without any acceleration. But for this particle, until this second, you cannot think of having terminal velocity. It was accelerating till that moment. After that, it tries to attain its it attains this terminal velocity and then settles. So, and it takes this much of distance to attain that terminal velocity. So if we now come to the effect of boundary, because all these thing that we have mentioned is based on the assumption that there is an infinite pool of liquid without any disturbance or the influence of the boundary or the solid boundary where the fluid is contained. For example, the room in the air, okay, if that is stagnant somehow, that without any fan, without any AC, any air recirculation is not there, assuming that if you if you leave a sand particle from the rest, this kind of measurement that we have mentioned is valid. But if let us say you take a test tube of a very small diameter, okay, and the particle size is comparable to that test tube size, okay, then the effect of the test tube glass walls becomes important. It influences the terminal velocity. Okay, so the presence of solid boundary influences terminal velocity, and the terminal velocity or the flow velocity inside such condition is lesser than the velocity reached by a particle in absence of this solid boundary. And this becomes particularly important for the measurement of viscosity by falling sphere method in the Stokes law region that usually happens in the Stokes law region. So what it has been done, people or the researchers have introduced a correction factor to the terminal velocity that is attained in infinite pool of liquid. Okay, so a correction factor has been presented, and the terminal velocity that is typically attained in the Stokes law region in absence of any boundary is multiplied with that correction factor, and then you get the fluid's ideal terminal velocity, not the actual one. Actual one happens in presence of the solid boundary. Okay, now when this solid boundary presence becomes important, as I said, the size of the solid particle and the size of the fluid container, if it's become comparable, okay, and how that is measured, like this is the factor that has been introduced by the researchers, is called the Wall factor. It is defined as the ratio of velocity in that pipe where you are doing the experiment to the velocity in its ideal condition, that ideal terminal velocity where there was infinite pool of liquid. So that velocity, which means the actual terminal velocity divided by the ideal one is equals to this expression, okay, is proposed by Ladenburg in 1907, where it was mentioned that this expression holds true when the x, which is the particle size or the particle diameter, divided by the tube diameter, this d is the tube diameter or the pipe diameter where that is flowing, the container diameter is basically less than 0.1. Beyond that value, okay, beyond that means if it is beyond this or it's a larger value, okay, then that means the particle diameter is smaller, either smaller or the container diameter is larger. If that happens, then this value becomes smaller and smaller. Okay, then the influences of particle this terminal velocity becomes more and more pronounced in case when it is becomes comparable. Okay, so for these ranges, several researchers have come up with the several expressions, like here this is proposed by Francis, where this Wall factor is having an expression of this. Okay, this typically this expression holds, I mean both the expressions holds finely accurate in the range of Stokes law region, which is the particle Reynolds number less than 0.3. Okay, and this particular expression holds true when it is in fact less than 0.1, with it happens with a better accuracy. Okay, so with this, if we quickly come to a problem statement to see that how these ideas are implemented or how these theories can be better understood, is that if we look at this problem, that what is the maximum size of particle okay, as a function of particle density for gravity sedimentation in Stokes law region. Okay. So, that is what is the biggest size of the particle as a function of its particle density, okay, that can settle in this Stokes law region for when that is happening in water and air at ambient condition. So, in that case we have to plot that maximum value versus its density in air and water, and considering the particles are of spherical shape. So, basically what that does mean, how do we find out that what is the maximum size that can settle under gravitational effect or gravity sedimentation can happen, because the maximum cutoff limit for the Reynolds number is 0.3 in the Stokes law region. So, basically we know the maximum Reynolds number, it can be of 0.3. Accordingly, X max has to be found out, or the maximum diameter has to be found out. So, which means the particle Reynolds number in this case is 0.3. This is the maximum cutoff value. Okay. So, that cutoff value is achieved by the largest particle size, because this Reynolds number is proportional to the particle size. Okay. So, if it goes beyond this value, this gravity separation would not happen in the Stokes law region. Okay. And now, if we assume that the rapid acceleration occurs because it is the highest size of the particle and it quickly attains the terminal velocity, then we can write this expression of the terminal velocity from the Stokes law that we have already known, that the particle diameter square in the Stokes law region relative density multiplied by g divided by 18 mu. From these two expression we can find out what is the value of X max, because here if we replace this u by ut, okay, we basically have an expression of X max in terms of this quantity. If you simplify this, you will get the X max value in terms of this one. Now, depending on the fluid property, because particle densities are mentioned, that is the range from 2 to 8000, we vary it from 2 to 8000 for a particular rho f. The rho f either can be the water or can be air. In both the cases, the densities and the viscosities has to be mentioned. Okay. So, for air, rho f is this one, mu is this one. So, we can find an expression of X max. Okay. So, here now we place from 2 to 8000, we get the value of X max. We can form a table of X versus the rho p versus the X for a known rho f. Similarly, for water, the density is this one and viscosity is this. These are we have received from the physical property table, or the data, these are typically will be given. So, you can find out similarly here the X versus rho p in this case. So, here rho f is 1.2, here rho p is 1000. We form the table. Now, the graph would look like for the water is something similar to this one. Okay. Why? Why there are two things, one is the rising particle, one is falling particle, because now if you look at the denominator, which is rho p minus rho f, rho p minus rho f, where f is 1000, but here problem says the particle density can be from 2 to 8000. 2 is greater than 1.2, which is the air density. So, in case of air, the particle will always settle, but in water, water density until it reaches 1000, 1000, those particles will not settle, it will rise. So, basically you have two different profiles here. So, until this particle density of 1000, you have such kind of a rising particle curve, because those particles, the lower density particles will come up to the water surface. The heavier particles, when it starts from the 1000, it will try to settle down. In case of air, as we have mentioned that point from 2 to 8000, which is always greater than 1.2, so it is always heavier than air, it will always settle through the air. I hope this is clear, this concept is clear. So in the next class we will come up with other several worked out example to clear all your doubts and the confusion if you have. And this brings us to the end of this present lecture. We'll see you next time with another lecture. Thank you.